Here we are once again back at the physics video lecture. Physics 107B video lecture 7. So we're working with the Maxwell stress tensor. We have an interesting problem to set up. I'm going to go back a couple steps and first of all just write this expression for the force. This is the total electromagnetic force integrated over a volume, and we have this Maxwell stress tensor. Gotta write the divergence here. Divergence v volume. Okay. And then we also have the pointing vector. So let's go ahead and put this in this form. Epsilon naught u naught ds dt, also d volume. Okay, so what do we have here? Divergence of this 3x3 matrix. What that means is we're taking the divergence as a row, if you will. So this would be a d over dx, d over dy, d over dz, operating on this, I'll just write it here, on this matrix. Okay, so row times column. Okay, so 3x3 matrix. We also can use the divergence theorem the way we always do, Gauss's, and turn this, because it's a divergence, into a surface integral. Now we would have the boundary of that volume, T dot dA. Point being that this is, since this is a vector, this is three integrals. The divergence hasn't turned the Maxwell stress tensor into a scalar, it's turned it into a vector because you apply the divergence 3 times. Okay. So here it's the same thing, but now we're operating matrix on a column. So in that sense, this one would be, and yeah, then we have epsilon u naught. We're going to deal with this one later. ds dt tau. Yeah, so over here, it would be matrix multiplication d ax, day, daz, and this would be, so this is row times column, and this here is row of your matrix times column for all three of those. Okay, this is going to make you appreciate this compact notation, because as you remember, there was so much going on here that we then, this immense expression when we had done everything, but it turns into such a simple form, divergence of this object here, minus derivative of the pointing vector. Okay, but now we're going to use this and do an actual calculation, and then the complexity comes back in. But right now we have a very simple notation. So our example is the force on the northern hemisphere or on the upper hemisphere for a charged sphere. So let's go ahead and just set this thing up here. This is all Griffiths, and I'm just filling in a whole bunch of missing steps. Okay, so what do we have here? Let's go ahead and start with our sphere. So x, y, z, we have a sphere of radius r, and the idea is it's a uniformly charged sphere. Uniformly charged, and capital Q, total charge, but of course a uniform charge of the same sign is going to have a repulsive force, and you can imagine what's the repulsive force on the upper hemisphere due to the lower hemisphere. So let's use a little extra color here. Okay, so we have separated that into two hemispheres, and we're asking what's the force on the upper hemisphere due to the lower hemisphere. So force on the upper hemisphere and it's just a uniform electric charge, so we would take F sub z. By symmetry, it's only going to be F sub z, okay? And there's no time dependence, so we're not going to have anything here, just the z component. So F sub z is going to be this integral dv, it's the upper hemisphere. And now it's the third, right? The third row times the column. So it's T Z X dAx plus T Z Y dAy plus T Z Z dAz. Okay. That's what we're going to have to construct. And I actually want to get it all on one board. So let's see if we, not all on one board. The ingredients on this board, then I'll send it up and do the rest of the calculations. So let's see what we have here. And I'll even write here, integral over the bowl and the disk. And it's pretty clear the bowl is this upper hemisphere here, and the disk is the z equals 0 disk. Okay. So that's our surface. We've got the bowl and we've got the disk, so that's what the integral is going to be over. So we'll have to actually do two integrals. But we have to construct all these things now. So let's see. May not all fit on one board. So first of all, we have to do tzx, dax, tzy, tzz, so we have tzx is equal to, and these we just get from the expression for Maxwell stress tensor. This is an off diagonal, it's just got ex, tzy, epsilon naught, ey, tzz, you've got the Kronecker delta now in play. You've got epsilon naught over 2 ez squared minus ex squared minus ey squared. Okay. And then we need the dA here, so how about we've got an r hat pointing out like that, and we've got a d area element. So dA is going to be r squared sine theta d theta d phi. That's the magnitude, and then times r hat. Okay, so that's our infinitesimal area times your r hat. Let's see what else we need. I could write the r hat down already. R hat is going to be sine theta cos phi x hat plus sine theta sine phi y hat plus cos theta z hat. Right, you recognize that, just the unit vector plane polar coordinates. Okay. Good. So what we need next, these are all of our ingredients, except we need these electric fields. Okay, it's not going to fit all on one board, that's the way it goes. So the electric field is a classic Gauss's law problem you've probably done before for the uniformly charged field. And we'll get the electric field. And then we'll have all the ingredients. So let's see. So let me consult here before I go on. A, we've got R hat. Good. So next, electric field of a uniformly charged sphere. And there's our uniform sphere, radius R, and we're going to use E dot dA over the surface there is equal to Q enclosed over epsilon naught. And our Gaussian surface is just some surface with radius lowercase, of a centered sphere of radius lowercase r. And so by the symmetry here we have E times 4 pi r squared. So electric field times surface, because of course the field is going to have to be pointing out everywhere by symmetry. The enclosed charge in that red sphere there, that would be the total charge (4/3) by radius cubed. Okay, that would be the charge density, total charge divided by the total volume times the volume of this inner sphere here, which is 4/3 pi lowercase r cubed. And of course we've got 1 over epsilon naught, which I'll put here somewhere. So we can cancel the 4/3 pi, 4/3 pi. What's going to be left is Q over 4 pi epsilon naught. When I solve for E, okay, I've canceled these 4/3. I'm going to be left with an R linear when I cancel that one there. So R over this R cubed here. Okay. And this times R hat. Okay. Now at the surface, okay, so this is within the entire sphere for any R. At the surface, lowercase r is capital R, and I have here at the surface, this is the one we're going to use first, E is equal to Q 4 pi epsilon naught R squared, because I've lowercase r equals capital R. Still times R hat. So those are all of the ingredients. And now that I have that, I think I'll just put that right here, and I can get rid of this. So we have E is equal to Q over 4 pi epsilon naught. I'm actually going to hold on to this one. R cubed R hat, and E surface Q over 4 pi epsilon naught R squared times R hat. So we're going to use this one when we integrate over the bowl, but we're going to have to use this one here when we integrate over the disk. So I think we have all of the ingredients. I'm going to erase this leave these up and then start, go to work on this. Good, yeah, and our goal is, of course, this entire integral. So we're going to construct these things here where we have all the ingredients in place. Do the integrals. What's going to happen is a large expression is going to boil down to a more compact one. Good. So here we go. And in particular, I'm really going to pay attention to this first one here. So TZX, DAX. Okay, so we have TZX, DAX. Everything's in place. So we have epsilon naught. Now we need E sub Z. Well, E sub Z would be, we're working on the bowl first, okay? The bowl. The bowl. Okay. Where are we here? Okay, TZX, epsilon naught EZ, and E sub Z is Q over 4 pi epsilon naught r squared. But that's just that magnitude. The r hat for the z component is cos theta. Okay. And then we have to do the E sub x. So again we have Q 4 pi epsilon naught r squared. And then for the sub x part of it, we have sine theta cos phi. Good? Yeah. And then we have the dA sub x. So the dA sub x is r squared sine theta d theta d phi. Let's make that r a little more legible. R squared sine theta d theta d phi. And then for the x in the dAx, we have to go to our r hat sine theta cos phi. Okay, so yeah, there's a lot going on. We have two more of these to do, and then we have to sum them up. That'll take on this form here. We'll have epsilon naught Q over 4 pi epsilon naught r squared. Okay. And then we'll have cos theta sine theta cos phi r squared sine theta d phi sine theta cos phi. So the other ones are going to be constructed the same way. This is dAx. Okay. So now we have T Z Y D A Y as our next one. T Z Y, excuse me, T Z Y D A Y. There's epsilon naught E Z E Y. So here's what we're going to have: epsilon naught Q over 4 pi epsilon naught r squared. Now we're going to have the cos theta for the z, and for the y we're going to have sine theta sine phi. So cos theta sine phi, and again we're going to have the r squared sine theta. Did I miss a d theta d phi? Yes, I did here. D theta d phi. D theta d phi. Sine theta d phi. And then sine theta cos phi. Here it's going to be sine theta sine phi. Now this one's a little more complicated, but we've got PZZ, PAZ, now we've got an epsilon naught over 2. So we'll go ahead and put that there. Actually, I consult here. Yeah, epsilon naught over 2. Again, this will be common, Q 4 pi epsilon naught r squared. And then we're going to have from the EZ squared, a cosine squared and minus sine squared, right? Good, cosine squared theta from the minus EX squared minus EY squared, so that's EX squared plus EY squared. When you sum these two up squared, these X and Y's, you cosine squared and sine squared add to 1, you get the sine squared. So that's why we have a minus sine squared. And yeah, and then the rest, yes, r squared sine theta d theta d phi, and then we'll have the cosine theta right here for the z component, because it's the DAZ, so this and then cosine theta. Okay, good. Those are all those ingredients. So I'll just write here, next, we have to sum them up in this form. And you see what we're going to have a lot of common, epsilon naught. When we sum this one up, we'll multiply this part here by 2. But the common r squared sine theta d theta d phi will be in there as well. And what happens when you take this, and then 2 times this here, you end up with cosine squared theta minus sine squared theta. I think I'll just write this out. Okay, what we'll do is we'll keep that picture there. That picture, and T dot D A Z component. So that's that sum of all 3 of those. Okay. We will have, I think I'll write it out first and then point at what we did here. So epsilon naught over 2, Q over 4 pi epsilon naught r squared squared. We have, gonna have to erase this. We have d theta d phi, sine theta cos theta, and everything else turns into a 1 times 1. So let's have a quick look at this. So what was common? Q over 4 pi epsilon naught r squared, we had that right there. D theta d phi. Actually, I better be careful here. I absorbed this r square into here. So this is squared and this is no more. Okay, that's how I got rid of that r squared. Okay, so we had d theta d phi, sine theta cos theta, sine theta Sine theta, cos theta there. Okay, so those were the common ones. And when you set this up, since we have, oh, pardon me. Okay, you set this up since we had the epsilon naught over 2, we had to multiply these by 2. And yeah, that's just a line of trig. They all add up to 1. I was wondering if I could see it immediately. Well, you've got cosine squared theta minus sine squared theta, sine theta cos phi. You've got sine theta, you got sine squared phi, cosine squared phi. You guys have a look at it. Go ahead and do it. It's actually just one more line. It's one more line. I'm tempted to write it down here. So here's what I'll do. I'll write it in red. So this one here was cosine squared theta minus sine squared theta plus 2. That's where I multiplied those by 2. Sine squared theta cosine squared phi plus 2 sine squared theta sine squared phi. And that does the trick, because the cosine squared sine squared phi gives you a 1. You've got 2 sine squared theta minus sine squared theta is 1 sine squared theta cosine squared theta equals 1. Bingo. Good. Good. So all we have to do now is integrate this thing over the bowl. And then we'll have done the bowl. So that can't be so bad. So integrate T dA bowl. We've got epsilon naught over 2, Q over 4 pi epsilon naught R squared. Here we can just do this eyeball on it. So the d phi, there's no phi dependence, so that goes from 0 to 2 pi. So we've got 2 pi. Sine theta cos theta d theta from 0 to pi over 2, right? It's the upper hemisphere. 0 to pi over 2. And the antiderivative is sine squared over 2. And so that's just going to be 1/2. Okay. So yeah, once you're here, you're in good shape. And now that cancels. What we're going to look for is to put it in the form of a q squared over 4 pi epsilon naught r squared and whatever's left over, okay? Because it'll be that, principally speaking, right? It's the force. And what's left over, we have one of the pi's, we had pi squared that canceled against that one. 4 pi epsilon naught r squared. Good, so we got an extra factor of 4. Epsilon naught canceled against that squared, so we have 1/8. Okay, so that's the bowl, and we now have to integrate over the disk, which is similar, but I'd say a little easier. Good, so I can erase all of this. We've got our picture up there. So the disk. That's the next one. Let's see what we have here. The disk. So for the disk, it's as though we were using plane polar coordinates, right? we're going from 0 to capital R. We're integrating over this disk here. So here's what we have. Here, dA, the only one we need, it's going to be z hat. So it's the outer surface normal. So we're going to have r dr d phi. That's what you have from plane polar coordinates. So we're just along the disk there, r dr d phi, and the minus z hat. Okay, that's the direction. E, which I have erased, but you guys remember it was that linear law, so q over 4 pi epsilon naught r over capital R cubed, right? This time we're integrating from R from 0 to capital R and R hat because it's pointing out. So E Q over 4, so here we go, 4 pi epsilon naught R over R cubed. And now we can use the X and Y components from plane polar coordinates. So we would have cos phi x hat plus sine phi y hat. That's where those come from, plane polar coordinates. And now this entire expression here reduces, right, that matrix multiplication that we did before, it just reduces to T, Z, Z, D, A, Z, okay? Because that's the only one of those three that's left. That's going to be epsilon naught over 2. So we're just going back to minus EY squared. That's the expression we had up here before with the DAZ. But now we have no E sub Z component, right? So we're going to have epsilon naught over 2 minus sine, and then EX squared plus EY squared. So EX squared plus EY squared, you've got your magnitude here, cosine squared plus sine squared phi, it's going to just be a 1. So that's that minus sign, so we have Q over 4 pi epsilon naught R cubed, square that, and then we have this R squared, and the DAZ is going to give us another minus sign R dr d phi. Minus R dr d phi. So this time we have to integrate this thing up. Okay, so integral d volume disk Z component. Let's see. I think we can just look at this one. The two minus signs cancel. We have epsilon naught over 2. We have Q over 4 pi epsilon naught R cubed squared. And we're going to integrate, minus signs are already gone, we're going to integrate an R cubed dr d phi. Again, no explicit phi dependence, so we've got the 2 pi right there. And then we have R cubed integrated from 0 to capital R. So that's R fourth to the over 4. R to the 4th over 4. So now we just have to clean that up and put it into this form here. So let's see what we have. Q squared over 4 pi epsilon naught R squared, right? R to the 4th over R to the 6th, that takes care of that. We've got the Q squared. We've got a 4 pi, and that cancels against that pi right there. pi squared cancels against that one. Got the 4 there, so we've got an extra 4. 2 against 4 leaves a 2, times 2 is 4, times 4 is 1/16. Okay, 1/16. Okay, so we've got an 1/8 and a 1/16, so that's 2 plus 1 is 3/16. Okay, so the grand answer here, finally, put it here somewhere. I'll write it in red. Did all that work for it? We have f z is equal to q squared 4 pi epsilon naught r squared times 3/16. There you have it. Okay, that's a really good example. Again, we started with that really compact notation. We had to fill in all the details, and we got a result that is just some factor times a standard Coulomb's law type of expression. Okay, let's see what else we have to say about that. Let me consult the clock here. Good, having done that, and like I said, that's just from Griffiths, but I filled in every step I could think of. Good technical calculation. Let's go back to our expression now for that force again. Go back to what we did. All right. So we're going to go back to, I'll erase that nice sphere here. Go back to that force expression and inspect it under a slightly different aspect. So we have force equals integral volume, or here's the question. We may just write both of them up. Well, okay. We're going to go back to the divergence later anyway, but yeah, so this is the flux integral, and then we have mu naught epsilon naught d s dt vector d tau volume. Okay, so that's what we had. Let's look at this under a different aspect. So it's force. We have these two integrals. We've actually done one of these here. No time dependence yet. But what about Newton's law? Okay. Newton's law tells us that this is the derivative of the total momentum. So this is d dt of the p mechanical. It's actually how we, that's how we got that. I'm going to bring this over to the left side and call it plus d dt p electromagnetic. And that is going to be equal to T dot D area over a volume. So yeah, this thing here I could actually U naught epsilon naught d over dt integral s d tau over a volume equals E electromagnetic. Okay. Remember, we were talking about the momentum in the electromagnetic field a week ago or so. So now if we focus on this expression, we see something interesting. Remember, these fields that comprise this go as the E field and the B field squared, okay? And the E and B fields decay as 1 over r squared, and the area is as r squared. That is to say, if you extend this volume to all of space, imagine you have a large sphere of radius r and let r go to infinity, so ball of radius r, let r go to infinity, then this integral vanishes. So the integral vanishes. Maybe there's a better way to write that. I'll just put this as a note. If radius r goes to infinity, this integral vanishes. Noticing I have a minus sign here that doesn't belong there. Okay. No minus sign. Okay, so if the integral vanishes over all space, then apparently you're looking at conservation of linear momentum. So this would be conservation of linear momentum, and you see linear momentum is conserved in all of space, but not in some restricted area. And we'll see later that's because momentum can be carried away. Okay, so actually we're already seeing a hint of it now. Momentum would be carried away by the fields when we talk about waves. Okay, but that's an interesting thing to see right here already. So let's put that as a note as well. Note, if this r goes to infinity, in other words, for all of, or how about I just write for all of space, we have conservation of linear momentum. So conservation of linear momentum for all of space. Right? Unlike in mechanics, where we have some restricted area where there's a set of particles whose linear momentum is conserved in the totality of it, here the linear momentum is only conserved if you're talking about all of space. Okay, the last thing we will do is turn this into another continuity type equation. So yeah, let's go ahead and erase this. And again, you appreciate the notation now. We just did a big calculation with this, but in this compact form, it says a lot. Okay, so I think we're just going to really introduce some nomenclature. So finally, let P mechanical equal integral. So the book just uses some cursive P instead of, d tau over volume. Same with the electromagnetic. P electromagnetic equal integral. This is mechanical. So this is some cursive P electromagnetic d tau. And then we're going to do the standard maneuver. We will have let's go ahead and do it. Then integral d, oops, cursive d, right? Cursive e, mechanical with respect to time, plus d cursive p, electromagnetic with respect to time. Minus my way here. Minus divergence of t. Doing the Gauss's theorem again. Okay. Bring that to the other side. T tau is equal to 0, arbitrary volume, and so we then extract out what's inside here. Okay. We'll do it in red. So now we have d mechanical with respect to time, d dt, d electromagnetic, minus divergence equals 0. We're accustomed to having a plus sign here, but that's just a sign. Or, plus the divergence of negative t if you want. But yeah, that has the same form as a continuity equation, which expresses a conservation law as well. Good. I think that's where we're going to leave it. Momentum flux density. Good. So next time we're going to do some more calculation with these things. But this is a good place to leave it. We did a static calculation with this object here, and now we've just reinterpreted it. And of course, we just did fixed charge, but there are charges, E fields, B fields, currents, the whole thing. There's a lot of stuff. Well, actually, E fields and B fields in here, and right, pointing vector right there. Good. So, see you guys next time.